This lesson is on graphing square root functions. So the first thing we're going to look at is the difference between a radical expression and a radical function. So a radical expression is an expression that contains a radical, such as a square root, a cube root, or an other root. So for example, something like the square root of 18. That is a radical expression that we would want to simplify. Or maybe the cubed root of 8n to the fifth. Or maybe the nth root of 9. All three of these are radical expressions, and this is what we've been working with for the last week. Now, a radical function will contain a radical expression with the independent variable in the radicand. So what this means is we're going to have two variables, an x and a y, an independent and a dependent variable. But what's important is that the independent variable, the x, is going to be underneath the radical. So for example, y equals the square root of x is a radical function. It contains two variables and they're related. Okay? You could also do the cubed root of x, or maybe even the square root of x plus 8. Okay, all three of these are radical functions because the independent, the x, is underneath the radicand. So the only radical function we're going to work with today is the square root function, and we're going to work at graphing these. Okay, we saved cube roots and other roots for Algebra 2. So graphing square root functions using a table is the first thing we're going to talk about. So the first thing you need to know is that the most basic square root function in the family of all square root functions is y equals x. Sorry, y equals the square root of x. Y equals x would be linear. Y equals the square root of x is going to be a square root function. So we're going to start by plugging some numbers into our table. So normally we would start with some sort of negative. So if we plug negative 1 into the square root of x, we would have the square root of negative 1, which we know doesn't work. Okay, this is not real. So we can't take the square root of negative 1. And if we went with more negatives, those would also be not real. So maybe we'll try the number 0 next. The square root of 0, well, 0 times itself is 0, so the square root of 0 is simply 0. That works. If we try 1, the square root of 1 is simply 1. If we tried 2, now the square root of 2, as we know, is not a perfect square. So this is actually an approximate answer, which is 1.414 and so on, if you were to plug this into your calculator. And one of the nice things about using a table is that you get to pick the values you're going to graph. And I don't know about you, but graphing 2 and then approximately 1.41421 is not a very easy point to graph. So instead, we need to pick values that are going to create perfect squares. So the next perfect square that would go underneath our radical would be 4. Because if I take the square root of 4, I would end up with 2. And then the next perfect square might be 9. So notice I'm purposely picking values that are going to give me a perfect square. The next one might be 16 or 25, 36, and so on. Knowing those perfect squares is very helpful to us. So when I go to graph these points, I'm going to graph 0, 0, 1, 1, 4, 2, and 9, 3 on my graph, just because those are the easiest points to plot. So 0, 0, 1, 1, 4, 2, and I don't think 9, 3 is quite going to fit. And if you'll notice, this graph has a slight curve to it. Okay, now notice I'm only putting an arrow on the right side because my numbers get bigger as they go to the positives. But I'm not putting an arrow over here. This point right here is my starting point. Okay, I can't go past 0, 0 because the negative values of x created not real answers. And all of the values on my graph are going to be real. So, one thing you might also notice is this almost looks like part of a parabola. In fact, if I were to draw this, it looks like a parabola turned on its side. That's because a quadratic, which is a parabola, the square, so an x squared and a square root of x are inverse operations. And since they're inverse operations, on the graph they almost look like inverse operations as well. However, the reason we only have one part of the parabola, we only have this this purple part and not the pink part is because that would create not a function. Remember that it would fail the vertical line test if it was truly a parabola turned on its side. So this inverse relationship can actually be seen. So now you can kind of see, well, there's my graph. It's going to be these 3 points that I can see on here, and it's going to have that same kind of curve as a parabola does. Now the next thing we need to talk about is our domain and range. So our domain for this square root function is going to create real numbers for x. So it's all real numbers because I could have used 1 and 1.5 and 2.3. I can use any value I want. I purposely picked 0, 1, 4, and 9 because they were simple. But I can't pick negative numbers. So what this means is x has to be greater than or equal to 0 in order to create a domain that works. And likewise, my range is still going to be all real numbers because even the square root of 2 is a real number. It's just going to be an irrational number. But my y values, notice that there's no y values below the x-axis. Okay, so again, notice this is with my starting point. My starting point starts at 0, 0. My domain and range also start at 0, 0. And I am going to go greater than 0 because my values for y keep increasing. Okay, so my domain is all real numbers greater than or equal to 0. My range is all real numbers greater than or equal to 0 as well. Okay, so now, this is the parent function. The parent function will always start at 0, 0, and then we will typically use the points 1, 1, 4, 2, and 9, 3. That is the parent function. But, as always, we can put other numbers with that parent function. So starting with number 1, our first equation in number 1 is going to be y equals 3 times the square root of x. So the first thing we're going to do is we're going to create ourselves a little table. So it's going to be an x and y t-table. Now, what number should be my first number in for x? Can I plug in -1? The answer is no. Again, it's going to create an unreal number in for x. So the first number I want to put in there is 0. We would have 3 times the square root of 0. Well, that's just 3 times 0, which equals 0. The next number that I would want to put in for x would be, again, 1. 3 times the square root of 1. Well, that's 3 times 1, which is 3. Now, I could put 2 in, but remember we'd have the square root of 2, and that's not an easy number to graph. So the next nice number I would want to put in is 4, because I would have 3 times the square root of 4, which is 3 times 2, or 6. And then finally, the next perfect square I'd want to put in is 9. 3 times the square root of 9, which would be 3 times 3, which is 9. So now we're going to plot our points. So we have 0, 0, 1, 3, 4, 6, and 9. 2, 3, 4, 5, 6, 7, 8, 9, 9. And that one actually did fit this time. And then again, creating this nice smooth curve. And notice this one moved up a lot bigger than my parent function. See how much higher it is? And hopefully you're realizing that this is due to the stretch. So this 3 right here in front of the square root of x is stretching my function. And notice it's not stretching it out longer, it's actually stretching it up higher. That's called a vertical stretch. Okay, that's why we call it a vertical stretch, because notice before I was going up 1 every time, and now I'm going up 3 every time because I'm stretching the graph vertically. Now again, we're going to do our domain and range. So our domain here is going to be all the real numbers. And notice again, we're starting at 0, 0. So x's are going to be all real numbers greater than or equal to 0. And y's are going to be all real numbers greater than or equal to 0. Now this time, instead of using our notation that we used on the parent graph, which is set builder, we're going to use interval notation. I know some of you like that notation better. So if it's all real numbers greater than or equal to 0, we're going to have a bracket on 0, and it's going to go to positive infinity with a parenthesis. And my range is also going to have a bracket on 0, and it's going to go to positive infinity. Okay, so that would be the graph if we have y equals 3 times the square root of x. Okay, so number 2, y equals negative 0.5 times the square root of x. So just based on the fact of what we're seeing here in front of our radical, this negative 0.5, hopefully you're thinking kind of to past graphs that we've done. The negative we would expect to reflect our graph, and it's going to do so. And the 0.5 is going to shrink our graph down a little bit. So again, we're going to use a table. So we're going to have a little XY table. And again, we're looking at values that can go in for x. So the values that can come in here for this x need to be perfect squares. So again, we're going to use 0, 1, 4, and 9. Those are numbers that create perfect squares underneath that radical. So we're going to have negative 0.5 times the square root of 0, which is going to be negative 0.5 times 0, or simply 0. Negative 0.5 times the square root of 1 is negative 0.5 times 1, which is negative 0.5. Negative 0.5 times the square root of 4 is negative 0.5 times 2, which is going to be negative 1. And then negative 0.5 times the square root of 9 is negative 0.5 times 3, which is negative 1.5. Okay, and you can use your calculator to do this. But if you know your perfect squares, it should be pretty quick to do using your head as well. So 0, 0 is going to be right here at my origin. 1, negative 0.5. So 1 and then down a half. Then we go over to 4, 1, 2, 3, 4, and down an entire 1 unit. And then 5, 6, 7, 8, 9, down 1.5. So notice, just like we anticipated, this graph is reflected, which means we're using the bottom portion of it. It's not up top here. So our normal parent graph goes something like this. So this one was reflected down over the x-axis, and notice it's shrunk down as well. It's not going up nearly as quickly as my parent graph does. So now again, looking at my domain and range, so this time instead of using interval notation or even using the set builder, which is again our parent graph, we use set builder. For number 1, we used interval notation. This time I'm going to use algebraic notation. So algebraic is where we simply write the inequality. So x, again, my x values are all greater than or equal to 0, but my range has changed. This time all my y values are below the x-axis, and notice they're all less than or equal to 0. So we're going to put less than or equal to 0. So hopefully you notice that by putting a negative in front of this square root of x created a reflection, and the reflection created a change in our inequality sign. So if there's a reflection, the y is going to be less than or equal to. Okay? All right, so let's look at number 3. Number 3 is y equals the square root of x plus 2. So what I want you to do is I want you to pause the video. I want you to create a table of this, write down your table, and graph this and put your domain and range using any of the 3 notations we just used. When you're ready, turn the video back on. All right, hopefully you're ready to now see the answer. So in your table, you should have had 0, 2, 1, 3, 4, 4, and 9, 5. Hopefully you used those nice points. And hopefully you were also paying attention to the fact that this was adding 2, which based on what it's done in the past should move our graph up 2 units, which it did. It took the parent graph, and which normally is here at 0, 0, 1, 1, and so on. It took this parent graph and it simply slid it up 2 units, as we should have expected. Now, the domain doesn't change. Our domain is still going to be all real numbers greater than or equal to 0. And again, I don't care what notation you use. You can use set builder, interval, or algebraic. From here on out, I'm probably going to use mostly algebraic because we are looking at all real numbers and it's quick to write. But what did change is our range. Our range is no longer starting at 0. Our range is now starting at 2 because our starting point moved. It moved up to 2 units. So you should have the range as y is greater than or equal to 2. So if you got this one correct, if you will give yourself a little smiley face. If you got it incorrect, give yourself a little frowny face and make sure you fix it. Okay, and a couple of things you need to make sure you're writing is make sure you have the arrow, and there's only one arrow. It's going towards the right side. Make sure you have your starting point at 0, 2, because without that your graph is incomplete, and make sure you have your domain and range. So now let's look at number 4. So number 4 is y equals the square root of x minus 4. Now this one's actually a little bit trickier. This is the only one that has something on the inside with the x. And again, if you will recall to past graphs, we probably expect this to move the graph left or right, because that's what usually happens when there's a number added or subtracted with the x, a horizontal translation. Now with this, that means we have to start at a different number, because watch what happens when we use 0. We have the square root of 0 minus 4, which is the square root of negative 3, which is not real. Okay, so no longer will our 0, 1, 4, 9 values, those perfect squares, work. So instead we have to figure a number out that's going to give us a perfect square. So our first perfect square is 0. Normally, what's going to create 0 underneath this radical? So x minus 4, if we want that to equal 0, what is x going to have to be? Hopefully you said the value 4, because 4 minus 4 is 0. So the square root of 4 minus 4, which would be the square root of 0, is 0. So notice our graph is now starting at 4, 0 instead of at 0, whatever that value is. Sorry, 0, 0. It's starting at 4, 0. Now, our next perfect square is 1. So how can I make x minus 4 be a 1? Well, the next value would be 5. 5 minus 4, of course, is 1. So the square root of 1 would be 1. Now our next perfect square is a 4. So what minus 4 would equal 4? Well, 8 minus 4 equals 4. So the square root of 8 minus 4 would equal the square root of 4, which is 2. Okay, what would the next one be? The square root of what minus 4? Well, 13 minus 4 gives us 9. So the square root of 9 equals 3. So again, the values we're going to graph are 4, 0, 5, 1, 8, 2, and 13, 3. If we can fit them all on here. So 4, 0, 1, 2, 3, 4. Notice it moved our starting point from 0, 0 to 4, 0. 5, 1, 8, 5, 6, 7, 8, 2. I can't quite get that last one on, but I do have enough points to show a curve. You do need at least 3 points. If we can get 4, that's even better, but at least 3. And that's our graph. And again, we anticipated that it would shift either left or right, and we should know from the past that when you subtract, it actually moves it to the right. So remember, it's our hips and our knees. Hips are opposites, so if it's a minus 4, it's going to go to the right. If it was a plus 4, it would go to the left. Now, our domain has changed. Okay, our domain is no longer at 0. Now it's been moved to 4 because our starting point has changed. And hopefully you've noticed that our domain aligns with our starting point. If you look over here at number 3, our starting point was at 0, 2. 0, 2 right here. And notice that our domain and range is at 0, 2. Okay, so here our starting point is at 4, 0, which means our domain is going to be x is greater than or equal to 4, because we're using numbers bigger than 4. And our range is going to be numbers that are greater than or equal to 0. Again, it corresponds to our starting point. Okay, now, this can be tricky, especially when you have other things going on. So you can use a calculator, and I will show you. So in the graphing calculator here, notice I've typed in the square root of x minus 4. And when I've typed that in, I end up with a table. And notice it says 0, 1, 2, 3. See how it says error, error, error? That's because those are values that are not real. This calculator is only going to give me real values because that's what we're trying to graph. And notice then you can look and see, okay, well 4, 0 is the first starting point. And then you can see 8, 2. And you can actually go through and find the exact values using your calculator if you need to. And then you can also see the graph and make sure it matches up. And notice my graph does look very similar. They're not perfect. My graph is more zoomed in than the calculator graph, but it's close. Okay, so you can always use the graphing calculator to help you find those starting points.